Hello, hello.
Hello, everyone, and welcome to the Builders Workshop. My name is Nathan, otherwise known as Old Man Builds. We have Sean Calderon here, and we also have the Benny Factor here. Guys, it's going to be an awesome show. Sean's got a cool presentation for everybody. What's up, guys?
What's going on?
Doing great. Can't wait to share some of the stuff that's in my lab.
Right on, man. Dude,
Ready?
this is going to be so cool. I got a sneak preview of his presentation, and let me tell you, it's awesome.
Oh, you're so nice.
Right on. All right, Sean, I'm going to bring it up.
Okay.
You ready?
Yeah. Thank you, sir. All right. So it's great to be here, guys. I missed you last week, and I've just been waiting to share all the stuff that I've been doing. So we're going to just see some coils that I've wound and how they function. And I'm picking this O-scope wave here because this is pretty much what the ZVS does to the Tesla coil. The outer wave pattern is the primary, and the inner wave pattern is the secondary coil. And so this is common, but I like to show what the waves look like so you can figure out if you're resonating. And let's see here. So I decided to roll 4 cone coils and then see if I can put them through experiments in different geographic shapes, geometric shapes, sorry. And so here they are. I winded 4 of them with 32 gauge wire. I bought this from Amazon. It's the cheapest universal rotisserie kit. And this is going to make sense here in a little bit. And so what I had done was I did a test to see if I could put epoxy on something that spins instead of having to put this my cone into a form and then put it in the vacuum chamber. And so here you can see that I'm testing the rotisserie here, and it looks like it's going to work here. And by the way, it's at a really good speed because when you're applying the epoxy, this speed prevents the epoxy from falling down, but it allows the epoxy long enough to really dig into the cracks and form a really nice coating. And so here now I have 3 shrimps on the Barbie here. And one of the things is that they're not going to continue to turn unless I do something to lock them in. And so I'm going to use the glue gun. There you can see the setup. All right, so I've coated them. And what's really cool about this is you put the coat on really thick, and then that's all you have to do. You're done. You come back in an hour or 2, and it's evenly distributed. It's worked its way into all the cracks and crevices, and it also gets rid of bubbles. And the reason why it gets rid of the bubbles is there's this sort of a lump of epoxy that travels around the cone. And if I were to stop this, then you would see a big glob come off of the bottom here. And so there's something about you being able to put way more epoxy than you could if it wasn't moving, and therefore it removes bubbles, it digs in your cracks, and it gives a really nice look to them. So here you can see them spinning, and I use glue gun to lock them in, but this is a setup. Another cool thing about it is I'm not hand cranking anything, and I'm not worried about anything because these things are going to come out awesome. I put R2D2's fume extractor here. That way, when I go work on the other side of my lab, I don't have fumes. So that's been really nice. And I think that's just another picture of R2D2. Yep. So here's a close-up. And so what you're seeing here on these cones is about 5,000 turns of wire. Now, you get this epoxy mess everywhere, And the only real way to get it off is to use nail polish remover or acetone. So I'll use a bit of acetone to wipe off my work area. That epoxy is just nasty stuff if it gets anywhere, because it'll absorb into that and then it'll get as hard as a rock. And so acetone is your friend. And here I'm wiping the bars from the rotisserie. I'm cleaning up my work area. The acetone fumes aren't great, so you should have a little ventilation. All right, my messy area here. So I hung them up here like Christmas tree ornaments. I hung them up a little bit premature because they're still dripping. So what I had to do is turn them over because it hooked on both sides, and it ended up working out nice. But they need to be more set before I hang them. Now this is a new approach I've tried. I've divided this coil into 3 sections. So the first section here is with 34 gauge wire. It's the red. This paler section in the middle is 33 gauge. And then this more goldish brass looking on the right, that's 32 gauge. So I thought, wouldn't it be interesting to have a Tesla coil that goes from thick to thinner to super thin and see what it does. So when you're putting the cone on the rotisserie or whatever you're covering in epoxy, you need to be level. If you're not level, then what happens is as you're turning it and adding a lot of epoxy, it's going to create a spot where the epoxy is going to leak instead of stay on. And so again, if you were to stop the rotisserie action for the coils, you would immediately have most of the epoxy drip downward. And so the spinning keeps it from dripping downward, but you wanted to drip it downward you want it to be on a level plane, so that way your epoxy is not thicker in one spot than the other. So here I show what I do. You work the epoxy in to the cracks, and that way then it'll seep in there, but you want to really get it a kickstart. And so here I'm just rubbing it in. Now I had been spinning the epoxy, stirring the epoxy for 5 minutes, because you must stir it thoroughly. And here they came out. They came out just looking like brand new. It's pretty amazing. And this is a lot faster because once you work the epoxy on the rotisserie, you just forget about it. That's it. And then you get this super beautiful shine, and it's functional, which I'll start to play with these in a little bit here. So I'm kind of showing you here my new ZVS coil on what the voltages are and what the wavelengths are, and I'm going to begin testing these little cone coils. One thing I noticed here is the ground on the cone coil is doing what that other cone did. It's arcing and sparking. That's peculiar. Normally the ground doesn't have this much energy to arc and spark, so I thought that was fascinating. So when you power up the oscillations, it should always be in milliamps. If it's not milliamps, if it's amps, you've burned something up. Here is Ian's capacitor board. This thing is gold. This allows me to tune in the resonant frequency. So right now, look, you can see the size of it. And as I'm adjusting the capacitance, it gets smaller and bigger. In fact, I can't even find a plasma discharge without setting these switches. And so we'll see a little bit more of that. So now what I'm noticing is that these cone coils aren't as peculiar as I thought, like the big one. Now I'm not completed testing. I haven't had a whole lot of time to test them. But what we're seeing here is I'm adjusting the cap box and able to get a nice discharge. Now, one of the cool things about the cat box is you don't even have to be staring at the plasma discharge. You can just hear it. And so as I'm flipping switches and listening, I can hear when it has the maximum discharge, and then turn around and see that it's pushed to its limits. So I'm gonna now see if we can take this child's picnic cup and use it to turn the triangle or the cone upside down and see what kind of functionality we get out of these coils. And I'll have to say, guys, unless you guys give me some good ideas, I haven't been very overwhelmed or impressed with them. I mean, they do some interesting things, but I had higher expectations, I think. So upside down, it puts out a pretty good amount of plasma, but it doesn't look outside the ordinary of what I've done with my other coils. So, and it seems like it likes to be upside down. Not sure why that is. And so I'm going to start with, again, the 12 volts, start the oscillation, then add the AC, and there. And you have to divide the AC in half because it's a half bridge. It has that diode. So let me see here. Yep. So it really wants to pull electrons from those copper spheres, which is really interesting. You never really think that it wants to extract electrons from anything other than ground, but it's not so. It wants to pull electrons pretty much off of anything that around it that can give them electrons, and copper spheres have a lot of electrons. This is something that was really new to me. I decided to pull one of my spindles of 5 pounds of 23 gauge wire, and I decided to use it as a ground. And I'll tell you what, I mean, it's a really good ground. I'm getting more out of the spindle of wire. I'm getting more of an output than I am with a ground. So that's really fascinating. This is it right here. That was my ground, and I start using this as a ground, and I guess it's going to be my new portable ground. Now the spheres work okay, but they seem to only work really well with my last cone coil, so it's almost like it's a certain geometry they like to play with. But when I use this spindle or this coil here, it's not a coil, it's oh boy, whatever this is called, of wire, it's acting like an amazing ground. And so I'm going to be using it as a ground quite a bit. And so here, it has that same effect from my other cone coil, where you look at the bottom, it starts acting like a bipolar coil because look at it's arcing in 2 different ways. So I guess that's unique to these. You look around and yep, it's going right to ground, but it's also creating plasma. All right, let's see again. That was quick. Yeah, no ground at all. And so that's the amazing thing about the triangle or the cone, sorry. You can do it without ground. It just works. You can't do that with any other coil, by the way. I've tried. Let's see here. Am I just trying to crank it up? Trying to figure out. Oh, I'm using the, so okay, it makes sense. So I'm getting a whole lot more breakout using this container spool. There we go, this spool of wire. All right, this didn't work, but it looked great. I thought I turned it upside down. So again, here's the wave pattern that we like. So normally it's a straight, consistent wave pattern with a squiggly wave pattern inside, but this waveform here forms when the cone coil is connected to ground, and when it's shooting off the ground, it creates these huge spikes. So it gives it that unique pattern. I thought that was interesting. All right, so look at all the space between the cone and this concave of pipe. It's a loose coupling, and these guys seem to really do well with loose coupling. They can throw out some serious arcs. This is no joke. They're really good at putting out some plasma. And these are 75% the size of my original cone coil, so these aren't that big, probably 5 inches tall. So this is some good plasma for 5 inches. And I just dialed it in with Ian's cat pack, and we're ready to go. I'm just trying one ice cream cone at a time, and this one seems to be doing really well. And yeah, I mean, with this much ability, we have to be able to come up with some cool stuff and figure out maybe to use them in some way to focus energy or focus power because of their asymmetrical design. So I'm not really sure, but I'd really like ideas from the audience. Oh, and I forgot to mention in the chat, guys, please put a question mark next to the items you want to discuss. I'd like to load the chat into a file, read through them, and then put them down as an action list, and then I can see if I can include your good ideas in my lab. All right, see again. Each cone looking great. This is just really testing how much can I push through them. What are they? How do they act? How do they react? I haven't done so much strange configurations yet. I was kind of hoping you guys could give me some good ideas with these. So I'm just doing my own same old thing, seeing how much plasma I can push out of this little guy. One thing I found out is there's a lot of amps going through this little hair thin wire. Why isn't it just burning up the wire? Well, I found out that there's something called Lorentz force, where as the electricity travels through the wire, there's an equal and opposite a magnetic field, pushing it in the opposite direction. So what happens is when the electricity comes through here, the Lorentz force pinches the energy to the wire. And so as it pushes, then the electrons just escape. Now, if the Lorentz force was not first, then this wire would be completely incinerated. So I thought that was fascinating, that there's a magnetic force that's pinching all that energy into that hair thin wire, pushing it. And then, of course, there's no place to go. So it starts going into the air, looking for a place to put their molecules. I'm sorry, their atoms or electrons. So at Starbucks, I picked up, not Starbucks, at thrift store, I picked up this acrylic sphere. I put tape on it because if you put tape on it before you cut it, it makes you have a clean cut. You don't have any cracks in it. I'm not sure if you guys are familiar with this tool here. It's an oscillating device, but it's the best tool I've ever worked with. I can cut all my fancy designs of my acrylic with it quite fast. And yeah, I saw a guy use it and I thought, where have you been all my life? Because this thing can cut metal, wood, plastic, and it's very precise. So I thought, okay, let's try these in the hourglass configuration. I was kind of rushing now because I barely gotten these cones finished before the presentation, but I thought I would just say, okay, let's try different geometric conditions. And okay, the slides are out of order. We'll get back to that. Sorry about that. And this is probably the fourth cone that I tested. Some of these cones are better than the others, even though I wound them almost identically. So I don't know what all that means, but this is pushing out a ton of plasma for this little cone, and it's different than the others. All right, hit the button. It's going to give us the milliamps, 160 milliamps to oscillate. And now I'm going to add an overlay of AC. It's always half. Well, this is going to be 10 volts. And then this is what it looks like. Now, this is one of the 3 different waveforms that I adjust to look at. And this is the normal one usually. So this consistent waveform is the primary. This in the middle here, this smaller that gets bigger and bigger and bigger and bigger, that's the secondary. And so this is another way to look at what the resonant frequency is. This is the one that I'm most familiar with. And so when you look for this, it's great. Now I'm flipping capacitors and it's making it bigger and bigger. And here I have this pathetic, it's just not really doing anything. What's going on is the primary of the bottom is powering this cone on the bottom. This cone on the bottom is then just going through the cone on top, and then see the alligator clip on the right, that's going to ground. So a big dud, nothing interesting. I really thought that there was going to be so much energy in here that it would have just sort of floated. I don't know. It's my overactive imagination. I'm a goof. All right, so now I'm putting them in a different configuration and not really doing anything crazy here. This is where I would love your guys' recommendations with these sizes. I guess I'm good at getting these things working, but I don't think I'm very good being creative to see how I can maximize these geometries. So I'm definitely open for suggestions. That would be great. So I'm just going to see what these cones can do in different conditions. I thought that was interesting. It has this sort of, I'm not turning off and on the power. I just turned the power on once and left it. But it has this sort of strange de-equalization where it shoots out and then it doesn't, and then it shoots out. It's almost like it's building up. And it's doing this thing where it's striking the bottom primary coil here. This is usually really bad, but for some reason I'm not having a bad time with it. Normally this should go back into electronics and burn a MOSFET or something, but it's not. So I hadn't stopped doing it because it wasn't doing anything. So I thought it was fun. So I thought, okay, well, let's play with it and test it. And the thing I wanted to test here was how they take turns and how one has a different color than the other. And it's so different because it's coming out of the same spot. If in this this hot glue, it is the center wire. So what's happening is that it's going out with the wire and then it's going out to do its own thing here on the copper pipe. So it's coming out of the same spot, but it's doing things differently. And so see. Oh, yeah. So it fascinates me that in proximity of things, you don't really have to be deep set in it. And in fact, Nikola Tesla writes about this, how in his high voltage coils, you don't need to have that tight closeness like you do with transformers and stuff that you find in electronics. He said it has to be a loose coupling. So this is a very loose coupling. The electricity goes down through this copper pipe bowl here, and it's just enough to kickstart this cone, and this cone starts to spit out plasma. So I think this is very fascinating how it sort of breaks the rules of transformers, and you can be sloppy. You know what? I don't want to wind a new coil. I'll just throw a cup in here and use this one, and you can do it. So I think here I'm flipping switches. Oh, no, I'm showing you how it arcs from both ends. Oh, the fun. Yeah, very destructive when you don't watch them. Let's see here. I think this is, we'll see. So here I'm doing more of the pumping in in the 40 volts range, probably 45 volts. So that's a lot, especially for these little cones. The only thing I could derive here, because these look similar to my other discharges, the only thing that I can derive from here is that's different is two things. It likes to strike the bar. As you can see, it's striking the copper pipe, and it's doing something else here too. If I pause it and pause it, what you're seeing is it has multiple streamers. When the other coils are, when you take a look and freeze the other coils, it's only one strand. And because that one strand sort of travels in different directions really fast, we get this idea of that it's like a bouquet like this, but it's not. It's usually one strand at a time. But this cone seems to keep it more than one strand at a time. So I thought that was fascinating. This is just me being silly. I threw some lights. Now, these cones aren't attached to anything but ground. So that I'm going with this cone coil here, and it has sharing a ground. It's lighting up all of these they're like 2-foot long fluorescent bulbs. But I thought it was interesting because there are just all of these things are grounded, and only the cylinder here is being powered up. And it takes a little bit to light up these 2-foot fluorescent bulbs because they go behind the LCD TVs, LCD monitors you get at the thrift store. And so they're not very bright. So they take a lot of power to get them to be that bright. So this I thought was interesting. Cones aren't connected to anything. So the radiant energy from the cylinder is exciting the cones, and the cones are just literally spraying the coil. So I thought that was kind of cool. Not sure. Again, the cones aren't connected to anything. Right. So I'm doing tests. So this cone here is starting to produce plasma. And look at that. That is so interesting to me. It's upside down and it's acting like a ground. And I can't tell if it's spraying the cylinder or if the cylinder is spraying the cone. I think it feels like the cone is spraying it. And then what's weird is it has that yellow hue, and you only really get that yellow hue is when you're running across ground. And so I don't understand, because this cone is not grounded, but yet it's giving you that yellowish breakout, and that you can only get when it's grounded. So I'm not sure how it's doing that. Pretty interesting. All right, so I wanted to, oh, wait a minute. Okay, so this is a tip. MOSFETs are electrostatically sensitive. And so if you're running your feet across the carpet and you decide to grab a MOSFET and spark it, you'll destroy it instantly. So when I start handling the MOSFETs, what I do is I'll grab a grounding wire and then handle the MOSFETs. And the grounding wire will ground me out, and I won't have a charge, and then I can handle them without an issue. Let's see. This is another miscellaneous. Trying to figure out what we're doing. I think this is another ground. This was that cool coil a couple of presentations ago. Yeah, so this is, I forget. I'm sorry, I forget. Well, it looks interesting. Let's see. What is this on the right? I should know this. Sorry, guys. I mean, it looks cool. Maybe I picked this up from another presentation. Yeah, that's probably it. Let's see. Trying to fix it here. It won't let me. Well, that's that hue that I don't understand. It's pretty cool looking. And usually that comes from a ground. Let's see here. All right. I think I took some slides from the other one. So these guys look, if they look familiar, my apologies. I'm just testing these copper spheres, and there are 2 breakout points for this older coil. And so I thought it's fascinating to see how it interacts with the copper spheres. It's a little bit difficult to work with spheres that are metal spheres because it so evenly distributes the charge. It takes more energy really to interact with them. And so it makes sense that they're only interacting with one instead of the second one. And I think the second one here is even closer. But once this discharges to one of these spheres, it just wants to stay with it, if that makes sense. Now it's creeping over a little bit. But I think that was the goal here of that testing. I think there's a little bit more of that testing. Let's see if it's worth watching. Looks pretty much the same. Yeah, switch. All right, so miscellaneous again. When you want to shape a concave coil, if you remember in my last presentation, I shared how you can use terminal blocks to fit the wires in between, and then you just zip tie the terminal blocks, and there you go, you got your bowl. Well, what I found out here is that you can still use the terminal blocks to space it out properly, but then you could just fill in the gaps with hot glue, and then you can remove the terminal blocks. You don't need them anymore because now you have a nice shape of a primary coil and you have no metal. It's just all hot glue. And so that's helpful because if you keep the terminal blocks, I've experienced this, the terminal blocks have metal in them. And so sometimes that metal gets hot because of the eddy currents from the secondary. So when it's arcing and sparking real big, it's causing eddy currents here in this pipe. And so if you have the terminal block, that is going to absorb that power in the form of and create eddy currents. All right, so this is the kind of stuff that I want to do when I read the chat. So 8th Sinner had mentioned if I can get metal to certain lengths, rods to a certain length, and then if I were to move them toward my Tesla coil to see if there is any different kind of properties from these lengths. So what I had done is I had pulled out my caliper, I had these aluminum rods, and I had a piece of sandpaper. And so what I did is I painstakingly would take off just a 1/10 of a millimeter and then put it in my caliper and go, oh, it's close. And kept doing that until I got 90 millimeters for this one. I tried to get a perfect 80 millimeters for this one, but I got 80.01 millimeters, and so that's good enough for me. I needed to get 80 perfect, but yeah, I just couldn't. And then this is supposed to be the one that has the funny action. And so this one's very particular. It's 88.28 and then 0 I'm expecting. And so this is not exactly what they said they wanted me to get to, but it was as close as I could do it with just taking off the slightest edge, the slices, and to get it this close. So I designed the 3 rods, and now I'm trying to figure out if putting out some plasma, is it going to favor one or the other? And so I really didn't see any of that as I was swapping these cups out and putting them in different positions. I wasn't getting anything different. They all pretty much acted the same. And so in pink, oh, that's pretty cool. The plasma's coming out the end. So the one that is supposed to have some interesting properties is the pink one over to the left. So the other ones I just color coded, but here we see that it pretty much acts just like all the other ones. So that's a kind of, I guess, since it didn't act differently, it's basically a fail, I guess. And so now I put the three together on some top of some acrylic container. And again, in fact, what you see here is it prefers the container than the rods. So plasma's fun. Isn't that cool? You would think that it would want to hit the rods, but plasma is a strange animal. Here I stuffed them in some styrofoam and kind of ran them by the arcs. And the special one of the pink over the right was supposed to do something special, and no, they all look the same. So I ran it through a little test, but these are the kind of things I'd like to do in the chat. Hey, try it. You know, in this instance, creating 3 different rods and see how they react to putting them next to plasma discharges. All right. There are only really 2 ways you can get an accurate reading from an O-scope probe. One is you dangle it like this. The ground is connected to nothing. The positive here, I put a little antenna here, but this is not connected to anything. And so the antenna will pick up the primary coil's output waves and the secondary coil, which is the cone. It'll put up the cone's waves. So this is how I get those cool wave patterns on the O-scope. Now, if I want a direct reading from here from the primary, I have to hook the positive and the negative. And as I hook up the positive and the negative, look at that. You get a nice sine wave. And so if you want to ensure that your ZVS is working properly, all you have to do is put a coil, a primary coil, and then put your O-scope, one lead connected to one side and the other lead connected to the other side, and then you'll get an accurate pattern. And it should look like this. Now, mine doesn't look a perfect sine wave, which is optimal, and that's because I got some noise going on. I got something going on that I have to fix, but this is good enough. This will work, so I don't want to discount that. If you don't have a sine wave coming out of your ZVS, then your ZVS is broken. All right, so this is that coil that I wound with 3 different windings. The top red is 34 gauge, middle is 33 gauge, and the bottom is 32 gauge. Here's what it looks like. Finished winding it. So this is something that was interesting. When I put it on the rotisserie, and I put on a second coat kind of late, and I came back and it had this sort of pattern in it. So I thought I'd draw out the pattern. It's hard to see here because I have to roll it closer, but it has this sort of S wave. And I thought that was interesting because it could have taken on really any shape, and it should have been equalized, but it didn't. It sort of created this sort of S wavy kind of thing. Oh, there's before I put the epoxy on. Here it is. There we go on the rotisserie. I can't say it enough. This method is so good. You just slap it on, and it will stay thicker than if you tried to paint it because of this movement right here. So, and what happens is you'll see a kind of wave, a hump, and it just rides down the coil, but the coil prevents it from getting to the bottom. And because it's riding, it's just pushing into each crack and crevice, and it pushes out bubbles. So this is a total way to do it on a budget with no vacuum chamber. Just buy the epoxy, get the rotisserie out, unless you can build your own motorized one. But I decided to get the rotisserie one because it has that really good speed. And boom, you're epoxying your coils like a pro. Here's how I got that weird shape. And I kind of was looking at it going, what is that? So pretty cool though. Came out really well. Really well. Look at that. Crystal clear. Now, it's important to note, look at how thick it is. If I stop this, all that would drip down to the tray. So it's just, I really like it. I don't know why it stays. It's like some inertia kind of thing or something. So this is the whole setup. I wanted to get an angle where you could see the coil in the middle of the primary here, and the capacitor bank, how it's connected, and then the ZVS circuit, how it's connected. And then I have this switch over here, and when I hit this switch, DC voltage goes over to my ZVS, and then it starts with the resonant frequency, which will show up here on the screen. Then after you do that, it has resonant frequency, it's already working. That's when you go to the variac and you start cranking it in. And what that happens is that as you crank it in, the voltage goes in at the resonant frequency and creates those big arcs. So here I am powering it up. You can see it's milliamps. Always should be milliamps if you're getting a good oscillation. I start turning on the variac, and as I flip switches, watch the screen up here. There you go. So you went from nothing to flipping the capacitors to get the right capacitance to, wow, right there, you have resonant frequency. That is one thing I really, the best thing I like about the capacitor bank. And that is, I'm so clumsy. Here we go. I want to show it again. So the oscillations are turned on. Boom, boom, good, milliamps, yep. Now it's time to crank the variac. And you look on the oscilloscope, you're getting something. Now I'm going to flip switches, and it's going to add capacitance. I'm adding more. Oh, there we go, resonant frequency. That's it. It's not harder than that. You don't have to play with clips, try to figure out where the clip goes here on the pipe, upper pipe. Nope. You just use this capacitor bank until boom, this is resonant frequency. Now maybe you don't want big plasma discharges. That's okay. You still need to adjust the cap board to get the biggest output, and then now you know it's in perfect resonance. Now if you don't want these arcs, what you do is you just turn the voltage up as high as you can without a discharge. And then what that's doing is it's going to start maximizing the radiant power, the radiant energy. It's not going to be wasted going out and looking pretty, but it's going to actually go through the air, that radiant energy to charge or power something. These things are works of art. Again, me and my googly-eyed photos of my coils. All right. So because this coil has 3 different gauges of wire, I thought I would test each side. So right now, the top side of this is the thinnest wire. So this is 34 gauge at the top here. The middle is 33 gauge, and then the bottom is 32 gauge. Okay, so that's, now I'm going to flip it over. I'm going to put the big wire on top now. This is the 32 gauge on top. I'm going to give it the same voltages. I'm going to give it the same everything. The only thing that I'm changing is the resonant frequency is different for the thicker wire than the thin. So I had to flip a few capacitors. But look at this thing. The thick wire at the same voltage is going crazy. You can already notice the difference. It has more energy, and it's reaching far. I mean, the fact that it's hitting the copper pipe down below and yet throwing our arcs largely everywhere else, it's so definitely, I would have thought it was the other way around. I thought having the thin wire on top would have been the best display, but not at all. thin on the bottom, a little thicker in the middle, and then the thickest on top. And bam, you got something that's just puts out the plasma like crazy. And by the way, all these experiments I'm doing on my new ZVS that I built and designed. So I'll be showing you that in a little bit. But it's indestructible. That's why I built it. But I need help with it. And I'll talk about that here when we're there. So I was trying to ionize my coffee. I thought that would give me a little more pep in my step. So unfortunately, I cranked up the voltage and it didn't want to go near my coffee. So that was a dud. All right, so this is something that I've seen is unique to the coil Teslas. Oh boy, the cone coils. It seems that plasma breaks off. And when I went back and looked at other videos, my other Tesla coils weren't doing this. In fact, only one other Tesla coil did it like once. But as you'll see here, I was finding them everywhere. This is another one. And I wasn't even going through that fast. So look, here's another one. They're just in the air. It's really strange. Here's another one. I can't wait to hear what you guys think about that. Now, this is another thing to show you how powerful this is. I did the math in measuring this. This is 15-inch arc. If you do that math, this is about 1,000,000 volts. So you're talking about incredible voltages on this little 4 or 5-inch cone. And I don't think I was getting this these long discharges on my other coils, not like this. Another, again, a lonely leg just sort of leaving, going its own way. If I had a high-speed camera, I would love to see like how that would propagate and move through space. But I just use my iPhone, so I don't have that functionality. Another one. Now this is the cylinder. I looked through every single frame of the cylinder, and it had one. So they happen very frequently in the cones, but this cylinder was able to give me one. And I've looked through a lot of these frame by frame because I like to look for cool photos. And this is the first that I've seen in any of my other designs until I went to the cone. The cone, they're just frequent. For some reason, I love the effect when it hits the primary, even though I know it's going to fry my MOSFETs. Okay, so I wanted a way to have a plug-and-play circuit. I wanted a way to just have things connect together, no soldering, just connect together and then work. So one of the things when you use a ZVS PCB or printed circuit board is that the traces inside are very thin. A trace is what connects the components and that are sandwiched in between in the printed circuit board. But if I connect everything with 1/8-inch pipe, then I don't have to worry about those traces burning out or breaking. So I was just fiddling, getting these things fitted out and see how they're going to work together. And so getting a proof of concept here. Even though all of the plasma that you saw earlier came from this ZVS that I'm building. So I'm kind of getting the cart before the horse here. Sorry about that. Here I'm setting it up visually. Something about 8-inch pipe is the holes always get pinched, so you got to kind of dig them out until you can fit in your components. But look at this. You can put a diode in there. Oh, we're cooking with gas. So you just start making geometric shapes. You can do a little bit of soldering, but not the components. So here I'm just building it layer by layer, piece by piece. pulling out these that I've got from old stereos, these heat sinks. There's some more progress. And now I do a little soldering because I don't have a pipe that can cut the corner like this. So that's fine. The pipe goes in there. Look at that, comes right off and lets you pull out the diodes as you need. And I'm using the heatsink as a brace but it doesn't really need it. But I thought it would work. I'm using the IRFP 260s. They're cheap, they're powerful, and so they're good all-purpose for prototypes. Highly recommended. And I do this little thing where I create a little alcohol bath because I don't like the resin. Makes it sticky. So I just put a little alcohol and get an old toothbrush and get all of that resin. So that way it's nice and shiny and bright and no goop. All right, here's what it looks like. It's so ugly. Look, it's my first one. So, hey, it does the job. I can put resistors in. So this is a faulty function. Look, I'm going to test it. This gives you an idea how it's plug and play. Yep, look, I needed a 10K. It's 9.99K. We're good to go. So it allows you to check your components super easy. And again, like I shared, all the powerful plasma discharges you saw earlier, they were all coming from this funny looking contraption. So here's what it looks like. It's it needs help. I need somebody who's organized or who can improve on when someone's done the hard work to get it working, but to make it pretty or streamlined. I was thinking maybe Nathan could help me out with that. He's pretty good, but I'm open to suggestions. So let's see here. I don't even know what we're doing. Oh, when this hits, look at the left, it turns into a skeleton. So I thought that was interesting effect. It was stripping it down on the left to the thickness of its arcs. And therefore, when you ground it, it changes the whole look. So I thought that was worth sharing. All right. This is my Uber circuit. This is it. I have a 10 component rule, and this has 10 components. I don't count these two diodes up here in the upper left because they're part of the power supply. The actual circuit is this. And I have spent months researching, looking at every kind of configuration you can do this. And I was stripping away things that you don't need. And I came down to this. And so you need 4 resistors, you need 2 diodes, and you need 2 MOSFETs. Oh, sorry, and you need these 2 toroid coils. So that is a total of 10. If you connect them this way, and I like the way they're connected here because it's not a schematic. It's literally, if you put your diode here, FR307, and your FR307 here, and you could just then build your copper connections and this will work. This will become your circuit board. So I'm really big on these because I'm dyslexic. I can't do real electrical engineering stuff. I got to do kind of this little kiddie version. But I feel like it helps for the new person that says, oh, it's only 10 components, and I just grab some wire and connect them this way. Yep. And then you'll have that powerful ZBS that you've seen push all that plasma during this whole presentation. It's all coming from this. Let me know, guys. I can message you a copy or however you'd like me to send it to you. There it is. This is the realized version, and it looks ugly, but it's functional. And I really can't wait to get help in making it look streamlined, because I think it's almost there. The nice thing is it works like a charm. I mean, it works well. And when it stopped working, I literally just pulled out the MOSFET, put it in my tester, and boom, I was back up and running. Now, if you want to know how it's working and what it's doing, then I created this diagram. But I don't want to go through everything here because it's a lot, but I wanted to kind of show you that it has 1, 2, let's see, 3, 4, 5, 6, 7, 8, 9, 10 components. That amazes me. That's so awesome. And literally, if it burns out, you're up and running in 2 seconds. You never have to worry about the wires because the wires are super thick. So here I'm showing you how you could just slip out a MOSFET and you're ready to go. Plug and play. And here I'm gonna pull out my MOSFET and test it. I love this little tester. It's actually an O-scope, but I use it as a tester. You don't even need to set it. It'll find what component for you. And here you have a good reading. That MOSFET works. So I'm looking to put it back together. And this would be part of streamlining it because, yeah, I can put it back together. It's plug and play, but it's not super fast right now. It needs a little bit of TLC. Sorry, 1 second. So something I didn't know about these 3-prong terminals, if you look inside of them, they're bent. So they don't stick out very far. Now they work great on a PC board, but what if I want to be able to use them for something like the Uber, my Uber, I called it Uber, the ZVS. So if you put your those pliers in here, and you can just press down, and then they come out quite a bit. So I don't know if you knew that, but this is a great addition because now you can do a lot when these leads are coming out great. And then all you have to do is put the MOSFET in here and tighten it down, and you're good to go. So one thing I did is I swapped these direct connections to the transistors, the MOSFETs, and then put in the green directly connected. And that way I can pull these MOSFETs out easier. But again, it's still super simple. Look at this. Again, that's super easy to do. And it's not hard to put it back. So I'm testing this one. And that's bad right there. Look at that. So when it reads it as a capacitor or an inductor or as a diode, those things mean it's bad. It needs to say MOSFET here. So this was the faulty component. I swapped it out real quick and we're ready to go. Here we go. It's not pretty, but it works. Hit the button. We got our 160 milliamps. Let's add a little bit of AC. Check out our wave pattern. It's always different. So this one, the primary and secondary are in the same mode of resonance, and that one's really cool. I don't know, maybe it has to do with this sphere. So I'm having a discharge here in this pure copper sphere. But what interested me in this clip was that it was still striking the downward toward the, I'm sorry, I'm having a hard time, guys. Striking down the copper pipe. Now, when the Uber runs, the Uber ZVS, the input diodes get hot, so you got to keep an eye on them. You don't want them to go over 120. Here we have after the board was running for a period of time, the Uber. And so these 100 ohm 10 watt, these guys are the heavy lifters, so they're always going to be warm. That, of course, on the left, that diode's going to be warm. And then you watch for other things. The chokes get warm, that's fine, because they can take a lot. It's the other things that you don't want warm. You don't want your MOSFETs warm. You don't want your diodes warm. Here's even a more close-up. I don't know what's going on here. All right, so here the Uber, you can see it up close. On the left, you have those powerful wire-wound resistors, and then you have the chokes, these these donuts here, and you'll see that the whole thing is running cool. Now, if you were to show this with the thin traces or thinner wires, they would get hot. So this is always going to stay cool for you. And so that's one of the other reasons I wanted to move to the copper pipe as connectors. And so here you see a top view. You don't even see the MOSFETs, which means this is running really efficient, because the MOSFETs only get hot when they're not being run correctly. So this is just a really good design for the MOSFETs. This is what Ian's cat bank looks like. And you'll notice here that it gets hot in different places. I want to open up the box to see inside, because this seems to be the pattern every time I use it. It has sort of this heat over here in the lower right quadrant. Hit another high level view. Here's Uber. Here's the cat box. And the leads to the cat box, you need thick ones. I didn't have thick ones, but you really need to try to reduce the heat in your circuits, because it's inefficient. It's just a waste of power, and it's hard on your components. All right, what I'm doing here, I think I'm done. I think that's the last slide. Yeah.
Dude, that's really cool, Sean.
That was one of your best presentations to date. I loved every bit of it.
Thank you. Wow, I appreciate that.
Hey, welcome back, Sean. That's a way to do it, brother. Give Sean a hand, man.
Yes.
Thank you, guys.
Such an amazing presentation. So many aspects of that presentation we need to go over, because there were so many cool parts, especially my favorite part, which was the way you utilize the mini copper tubes. I love that. It's so smart, and it looks nice. It looks so aesthetically pleasing.
Thank you. I appreciate that. I've been beating my head against the desk for months to try to find out plug and play. And you know how you'll just get on a circuit board and put a lot of terminal blocks on it, and
Sure.
it never comes out right. And then you're pulling your hair out.
Oh, wow. It's a brilliant solution. And then the other solution you had earlier in your presentation with the resin coating, that was also brilliant, using the rotisserie chicken setup. Oh my God. Like that's absolutely mind-blowingly brilliant. I loved it.
Thank you.
That was awesome.
I hope it makes it accessible, because it can be intimidating to get a vacuum chamber and to get all this extra equipment when you just need a little epoxy and turn at the right speed and just packing a big glob on it, and that big glob will stay on it.
Well, let me tell you, it made it less intimidating for me. I sat there and I was like, I can do this. If I have the proper setup in a little space, I can do this easy. You know, that's and before I was like, I might not be able to do this.
Oh, that's awesome. Thank you.
Hey, Sean, how fast does that rotisserie thing go? Is it a lot faster if you turned it up?
So if you buy one as cheap as mine, no. It's just one speed. But if you buy one that's a little more expensive, then they have speeds. Mine doesn't, because it's El Cheapo.
Oh, I was just wondering, you could literally take one of those and wind a Tesla coil with it, if you can, put on the ends to it.
Right. That's right.
3D print the end parts, and you're good to go, man. You can wind testicles all day long.
Isn't that crazy? And it's totally made with spacers and everything for whatever you want to put on the rotisserie bar. It's really so you can scale it. You can make it small or big, but it's gotten rid of a lot of headaches for me, because the forms are tough. You have to use a spray agent. You have to use your heat gun to get it out. You have to sand the parts, and then you got to put a spray coat on the sanded parts. Then it never comes out right.
Well, that's working against gravity. What you're doing now is working with gravity. You're just using gravity to let gravity do all the work for you.
Perfectly said. Exactly.
So, Sean, one thing I saw people do, you know those little heat guns that you can get? Use it for your circuit boards and stuff. Mm-hmm. You can use one of those to pull out the bubbles in epoxy when it's rotating.
You know, I've seen guys do it with a torch, but I didn't know you could do it with a heat gun.
Yeah.
Oh, that's great. What's strange though is I watched it as it spin. It was pushing the air bubbles out to the surface, and it was drawing in the epoxy into the wires. I just thought, oh my goodness, it came out so nice. I was surprised.
Yeah. Oh, it looked really good. It's probably less of a hassle than tearing off PLA when you're done.
I know, exactly. And scraping and sanding and oh boy. Less of a hassle than tearing off PLA. Sorry, I just turned on my iPad. Oh. I like to read the comments on my iPad side. All right. So do we have questions in the chat?
Let me see. Hold on a minute. I'm reading it. How do you splice the wires together, Sean, when you did the 3 different wires?
Yeah, good question. So I strip about an inch off of each end. I scrape off the enamel, and then I'll twist one around the other one. So one stays straight, the other one winds around it on the straight piece, and then I put a little the flux on it, and I'll run my soldering iron. I'll put the solder on the soldering iron, and then I run it up and down, sort of like I'm kind of scrubbing it, and then I pull away, and you have the thinnest coat of solder that as possible, and it just tucks right into the groove, and then I go winding again.
You don't try to clear it with anything?
Clear it with anything?
Put any kind of coating on it or anything else? You just
No, thank you for that. I'll take a cotton swab and alcohol, and I'll take off the flux. I'll wipe off any of the gunk and stuff, and I just tuck it right into the groove, and I'm winding again. And I learned that way. And people just say, well, why don't you splice it and only leave maybe just an 1/8 of an inch of touching each other? And I found out, no, you want a good inch. And the reason is you're going to it's not going to be a spot where it has resistance. It's going to be a spot that has less resistance. So that's why I do it an inch on each, and then wind them that way.
Very cool. Okay, the spool that you had set up, was it grounded as well, or just the spool?
Ungrounded, just the spool.
That's awesome. I gotta try that.
It's so crazy. I thought I got all these items that have electrons in them. I wonder if they want to give them up, and they do.
Oh yeah. Let's see. Do you have different sounds when you give different color discharges?
So that's a really good question, because you do get different sounds based on how close you are to resonance. And they have to do, what they're going to do is they're variations of the 60 hertz that's in your wall socket. Because what happens is that the half bridge power that comes in is a 60 hertz positive pulse. Positive, it's a pulsing DC, if you will.
Mm-hmm.
And so it's called the 60 cycle hum. So there's 3 noises it has. It has this really loud, grumbly sound. It's horrible. And usually it's associated with when you crank it all the way up and get maximum plasma, that it has that really obnoxious loud sound. Then there's just the in between, the hum, and then there's a almost quiet. It's a hush. It's barely a shh. And when you get the hush, you're really at the maximum of pure resonance. I thought pure resonance would be the loud one, but now that I'm playing with the capacitor board, I'm finding out that when I get perfect in the resonance, it just goes quiet. And it's really amazing. Yeah, it's really amazing.
That's cool. I obviously can't hear, so I don't pick it up. Okay. Pyramid. You wound a pyramid a little while back and ran it, didn't you?
I did. I put it on the shelf. I'm a cat with a laser pointer. I know. That'll come back. I'll bring it back. But yeah, I have one.
Okay, I want to say thank you to Chris Hayes. Awesome, brother. You gave out 2 gift memberships right here, 1 and 2. Very cool, man.
Thanks,
Thank you.
Chris. Nice. Awesome. Appreciate it.
We also got to use metal plates in between, and I think somebody put it in there. You 3D printed your plastic to go in between.
So the coil, the cylinder, and the cones are 3D printed with standard PLA, and then I use 32 gauge magnet wire, so the enamel coated wire. Now, what was the other part of the question? Metal plates?
Oh, he was asking if there were metal plates in between each one, but like you just said, it was plastic.
Right, it's just plastic. Mm-hmm.
Okay. Put it up. Why wire with more thickness than MOSFET leg thickness?
Why wire? Oh, he's talking about the copper pipe. So I'm using the copper pipe because you get large currents and you don't have to worry about your wires burning out. So that I use the copper wire. That copper pipe will never burn out. I mean, that copper pipe is like 100 amps or more. So it's thin, it's malleable. The holes in it perfectly fit components, which is nice. So you can slip and slide components in and out of it real easily. So yeah, all around that copper pipe was the best. Michael Merrick has a question. Primary to secondary needs to be primary 1 to, I'm sorry, it needs to be secondary to be 1, primary to 100 secondary windings ratio. Are you just using random numbers? I'm not sure what the question says, but I think I know what he's saying. So yes, the primary has a few turns, and then the secondary has many turns. So it's a step-up transformer. I don't count my windings. Some people do. I just go by the length and the gauge of the wire. I know Ian counts his windings, and so he always can give you an exact ratio. So, and also too, when I built the cones, I was weighing them because I wanted them to be the same volume, have the same amount of copper. So I did things like that to kind of make them consistent, but I never did a complete ratio like you're asking here.
Okay, can you use Teflon insulated wire for the secondary and not use epoxy?
If you used Teflon, you would have to put a few turns on, then add Teflon, put a few turns of wire, add Teflon, put a few, because you couldn't take a whole 200 windings in a groove and just cover it with Teflon. What's going to happen is that it's going to break right out of that groove and go right through the Teflon as if it weren't there. So yes, you could use Teflon, but you'd have to add layers and layers and layers, and it would be a very long and tedious job.
It reminded me of, I was reading an article with a coil, and they said Faraday took his wife's something from her dress and wrapped it around the wire in order to get insulation on it.
Oh, wow.
Yeah. Things they did back in the days, man. Creative like us.
Yeah, right. We are the garage door, garage scientists.
That
Lots of
dress
time.
must have been electrifying.
Yeah. Right.
So it says right here, the sound would be lessened if you use a diode bridge, 4 diodes, and some smoothing caps.
That's true. But you wouldn't get the big lightning bolts. You wouldn't get the big lightning bolts if you smoothed out the DC. That's why I love the half bridge, because it's real bumpy, and therefore it puts out lightning bolt shapes. You guys know when I do the pure DC and it's just a big puffy ball.
Mm-hmm.
If I did the 4 diodes here and a smoothing cap, all you get is the puffy ball.
Oh.
If that makes sense. So it's a good idea, Taryn, visitor. But I just didn't want to do that for this purpose, because I wanted to have that lightning bolt shape effect. But your idea would work. Let's see. Is it easier or harder to initiate electrolysis with energy you guys are making? Harder. David Williams asked this. Is it easier or harder to initiate electrolysis with the energy you are making? Electrolysis. I'm trying to think of what that means. Is that when you use electricity to, I forget, to
It's to break things apart in water.
right, there you go.
Yeah.
Like batteries.
Yeah.
I'm not sure though how electrolysis applies here. Nathan, what do you think?
I wouldn't use it for electrolysis. I'd use something very simple like 5 volts. Just straight out electricity would be able to do it and break things apart. Would it go faster with the higher voltage? It probably would. It also make it, a little bit more going on in your container, but it'd definitely work.
Yeah, that's true. Chris has a question. If you have a drill press and a 1/4-inch copper bar stock, you can make press fit 3-way connectors and 90-degree connectors. Yeah, I mean, that's going full Lego right there. That's a good idea. Where you make 3-ways and 3-to-1s and 2-to-3s, and I mean, that's a really good idea.
Some of these things, like Ben was saying, just art form. When you start putting them together, they are functional, but they're just totally art. It's like pipe art. You know what I mean? They use it on
Right.
tables
Yeah.
and stuff like that.
Steampunk. Yeah, very cool.
It does. I'd like to have it organized steampunk. So,
Well, you've inspired me to try to do something with a lumen lamp like that. I don't know, organize the wiring maybe with copper tubes like that.
yeah, and it's the cheapest copper tubing on Amazon, so it's a win-win.
Whoa, sorry. What was the diameter of that copper tubing?
1/8.
1/8. Okay, I thought it was
Yeah.
1/8.
And you said you had to drill it out a little bit?
The holes are in there because it's a coolant. Some kind of coolant goes through that, so it is a copper pipe.
Oh,
But
so the transistor will just fit like without any kind of adjustment to it.
exactly, just fits right in. All your
Nice.
components slip in and out perfectly.
That's so convenient.
Yeah.
Yeah, because the jumper cables I work with, they're all loose sometimes, and they're sometimes they break apart or they fall apart.
Right. It's I call it my indestructible ZBS, because you can't, once it's wired with copper pipe, it's done. You just now swap out broken components when it happens. That's life. So, but the structure is solid. So 8th Center asks, the small coils also appear not have any broken charge or internal charge leakage going on. Is that the case? Ooh. Not sure what that's asking. Ben, Nathan?
I didn't see the comment. What did it say again? One more time?
8th Center, the small coils also appear to not have any broken charge or internal charge leakage going on. Is that the case?
I'm not sure what that means.
Yeah.
Do you not get all the messy breakout in between the windings with all those small coils? Is it better?
I'm not sure. What did you guys think of the lonely plasmas, where they were just in space with nothing connected? The photos I showed, what did you think of those?
I think that's awesome, Sean.
I honestly don't know what to make of that.
Yeah, I didn't either.
That's warranting further investigation for sure, because I've never seen anything like it.
Yeah, I haven't either. And I scoured and looked for the other. It's weird that it happens the most with the cone too. That's what kind of seems strange.
It's that shape. Something to do with that shape.
Yeah.
By the way, Jarvis, real quick, I did send you the invite. It's on your Facebook. Hey, real quick, Sean, you always show this. You do notice that when you get the tendrils that come up, the swirling plasma,
Right.
that's the only time that you're getting that ground to pull in.
Oh, interesting.
It doesn't do it with regular Tesla coils, the way they run. You're inverting a field somewhere.
Very good. Right. One thing, please, you have to be careful with it all. It can damage your DNA. We use huge coils in our cooling towers to break down DNA and bacteria rather than using biocides. Look up Pure Pulse. No way. Look at this guy. ZZ Top. He's here.
What's up, Jarvis?
Hey.
Hey, I was getting delayed because I was playing live stream at the same time, but now I'm good. What's up, everybody?
Look at your setup. Awesome.
Yeah, I'm trying to get going. Trying to actually start making some real videos on my channel instead of just no narration, quick videos to kind of put it into place of what I'm thinking about going towards. I'm gonna go ahead and mute for a second, let you guys chat. I'm in the middle of something, so I'll be right back.
All right. Sounds good. Well, we got questions. Somebody mentions DNA being damaged.
Hold on. Stop. I'll stop you right there. We're not going into medical.
Oh, good catch. Thank you. Thank you for stopping me. All right. Here we go. Creative Studios, for some reason, it reminds me of a snake on a plane.
By the way, right here, Mr. Lanius is Jarvis.
Yeah.
You guys didn't know. So
Right.
now you know who he is.
Yep. Super cool. So Ben, do you have some stuff here, or before we
I got a couple.
ZZ Top?
I got a couple of updates. Been messing around with the Dual Thief setup, specifically to try and close the loop We're doing some testings with closing the loop now. So our measurements show us that we're getting, like, with the 40-watt panel attached, about 37 to 38 milliamps coming out of the battery. And then coming out of the coil, we're getting the same amperage while stepping up the voltage quite a bit. So the problem is the circuit itself seems to be either wasting or losing at least 25 milliamps of that, because only about 10 milliamps is actually going to the load. So what I'm trying to do, I've been focusing, lately on trying to get that to stabilize, and we've gotten it to stabilize with the 0.6 watt LED, where it goes down to 10 milliamps off the source, and it's actually putting in the same into the load, which is pretty cool. So that's pretty efficient, but it's very low lighting. So
Yeah.
I'm trying to tune the system and get the most out of it. And right now I've switched my focus to trying to close the loop with the pickup coil using the dual thief setup. So it's basically using a dual thief, lightning thief device on one coil attached to the battery. And then you have another coil sitting below it, just, touching it, picking up the wireless energy that it's putting off into another dual thief circuit, which is amplifying that. And you can see the light on the secondary unit, like the neon excite. So it's, getting high voltage. And then I measure that coming out of that's using the open circuit method of the lightning thief, the PCB board version. So measuring the voltage coming out of that with a 330 picofarad capacitor in parallel with the load, we get about 30 volts.
Hold on
And
a
I'll show
minute.
you a video.
Uh-huh.
Sorry, Ben, I got to interrupt you. Sean,
Yeah.
you didn't have to do that, brother. You are the coolest guy in the world.
Oh,
man.
wow. Yeah, we got to give a shout out to Sean. Super
Oh, it's
sticker time.
nothing.
Thanks,
Oh my
brother.
God. Yeah, that's amazing. This is
You guys-
it's good to see such a community effort here.
I owe you guys such a huge debt of letting me be a part of this. This is just nothing compared to what you guys do for me.
We owe you the
us
debt.
nothing. Yeah, we owe you.
Yeah, you got to remember that we owe you.
So you owe me a smile. That's it. All right. Jar Jar, is he ready? He looks like
Let me unmute. I've got a roommate that's slightly deaf, so the TV is kind of loud in the background right now, but I'll try to keep it muted and not have too much interference. I did just publish a video, though, if you wanted to show it, Nathan.
Yeah, I'm going to bring it up for you. I was waiting for you to let me know you wanted it up.
awesome.
And then I can kind of comment on it afterwards if there's any questions.
Yeah, 1 second.
What's up, YouTubers? I hope everything's tubular. This first episode in the Keys to Free Electric Power series discloses a little-known method that's common in over Unity systems that I like to call boost belling. Many people are unaware that if you charge a capacitor directly from a power source, such as a battery, the maximum energy stored by the capacitor will only be half the energy that was provided by the battery. This is known as the capacitor charge paradox. And a solution to this paradox is using a boost conversion method to charge the capacitor to a higher voltage. An easy way to boost the voltage on a capacitor is by adding an inductor and diode in series with it. And with ideal components, this would double the voltage on the capacitor. Since the energy stored by a capacitor is proportional to the square of its voltage, you get roughly 4 times the energy stored compared to just charging it directly from a battery. Due to the resistance of the inductor and the voltage drop diode, there will be less than 4 times the energy stored, but you can easily get greater than 3. The point is, you can leverage the energy stored in a capacitor by using a voltage doubler or a boost converter. This is the first step in the boost belling method. Before we discuss the Belling stage and the method disclosed, it's important that we briefly discuss the difference between energy and power. Although the energy stored by a capacitor will always be less than or equal to the energy provided by the battery, the power relationship between the charging and discharging of the capacitor is not a conserved quantity. Power is the slew rate of energy. It's dependent upon the rate of change in energy relative to time. Some examples of mechanical systems where the output power is greater than the input power include mousetraps, crossbows, and slingshots. The reason these have more power output than their input is due to the relatively slow rate in the increase of their potential energy compared to the rapid transformation of this potential into kinetic energy. In other words, the slew rate in their energy input are less than their energy output. When you study Tesla's patented methods of power magnification, you can see he took advantage of this principle by always boosting the voltage of his capacitors to a high potential before rapidly discharging them into a high-frequency tank circuit. In an article written by Tesla that was published by the Electrical Engineer, there is a section where he said one may take a condenser, small enough to go in one's vest pocket, and by skillfully using it, he may create an electrical pressure vastly in excess, 100 times greater if necessary, than any producible by the largest static machine ever constructed. Or he may take the same condenser and, using it in a different way, he may obtain from it currents against which those of the most powerful welding machine are utterly insignificant. Such results are obtainable, and easily, because the condenser can discharge the stored energy in an inconceivably short time. Nothing like this property is known in physical science. In a lecture given by Tesla, entitled On Light and Other High-Frequency Phenomena, Tesla states when working with currents discharged disruptively, the element chiefly to be considered is not the frequency, as a student might be apt to believe, but the rate of change per unit of time. Frequency alone in reality does not mean anything, except when an undisturbed harmonic oscillation is considered. This is the most common misunderstood principle that I see in alternative energy communities. Many of them try rapidly switching their systems using transistors that are driven at the same rate as their system's resonant frequency. Common examples of these types of systems are Joule thieves and Slayer exciters. Transistors didn't exist when Tesla was alive, and if you use them in true Tesla systems, they will just explode. Most Tesla enthusiasts know he said to focus on energy, frequency, and vibration, but they are rapidly tapping their bells at high frequency instead of striking them periodically and letting them naturally vibrate. The difference in efficiency is similar to a guitar player that tremolo picks their strings at the same rate of the pitch they seek, compared to another player that simply plucks the strings and allows them to freely resonate. Tesla's principle of vibration is the Bell stage in the boost Belling method. In Tesla's patent entitled Art of Transmitting Electrical Energy Through the Natural Mediums, he states, in order to magnify the electrical movement in the secondary as much as possible, it is essential that its inductive connection with the primary should not be very intimate, as in ordinary transformers, but loose so as to permit free oscillation. That is to say, their mutual induction should be small. And I have found it practicable to produce in this manner an electrical movement thousands of times greater than the initial. That is, the one impressed upon the secondary by the primary. And I have thus reached activities or rates of flow of electrical energy in the system measured by many tens of thousands of horsepower. In the transcript of an extended 3-day interview of Tesla that was conducted by his legal counsel for his testimony in impending radio patent cases related to this patent, Tesla stated, I charged the condenser with 40,000 volts. When it was charged full, I discharged it suddenly through a short circuit which gave me a very rapid rate of oscillation. Let us suppose that I had stored in the condenser 10 watts. Then, for such a wave, there is a flux of energy of 40,000 squared, and this is multiplied by the frequency of 100,000. You see, it may go into thousands or millions of horsepower. During his testimony in court, under the penalty of perjury, Tesla stated, by certain novel processes, the energy of 100 horsepower will be used so as to deliver into the earth power at a rate of from 5 to 10 millions of horsepower. Assuming the lowest output value of 5 million horsepower stated by Tesla, this is a power magnification of at least 50,000 times over unity. So, now that you know that you can't use conventional transistors in true Tesla systems, How do you get your tank circuits to freely vibrate using the boost belling method? The easiest way is to like and subscribe to this channel. But the way Tesla initially did it was with electromechanical relays and segmented commutation methods. Most people don't know the very first patent that was issued to Tesla was for a commutator. He then explored rotary spark gaps and spark gap quenching methods. Since he knew efficient switching techniques were a key factor for his power magnification methods, he patented a long series of what he called electric circuit controllers. These electric circuit controllers were optimized for the production of the renowned standing waves and continuous undamped waveforms in Tesla's true electric power magnification systems. In part 2 of the boost belling method, within the keys to free electric power series, I'll show you how you can use a pulse width modulated relay as an easy modern-day alternative for Tesla's electric circuit controllers. I'll also show you a simple vacuum canning method that you can use that makes them silent and more efficient. Most of you watching this video that have been participating in Nathan's live streams on his Old Man Builds channel know that I am a big fan of relays. It's been assumed that they are way too slow to produce the high-frequency currents that are associated with modern Tesla coil replications, but they are not aware of how to use them the way Tesla intended. Thanks for watching, stay tubular, and please like, comment, share, and subscribe to stay ahead of the curve with anti-gravity and over-unity power systems.
Any questions?
Oh my God. Hold on. I'm trying to click every button. Trying to get everything done. Dude, that was totally awesome video, man.
Well
Thank
done.
you, bro. Thank you. There's many to come. That's the first key.
Wow.
There's so, but I think you get it. I tried to subliminally show like him with a baseball bat and a bell. It's not, and I can quote like low frequencies he said was more efficient because those frequencies he was hitting like a bat and bell. He's allowing the tank circuit to naturally vibrate, and you can only do that with like a relay or a commutator or a solid break and make kind of switch.
Yeah.
You need that.
I like the AI
generated.
generated photos. Those were fun.
Yeah. That's a lab from Google. I was able to use those. I don't know if they're going to start charging in the future. I hope not, but Google Labs has some really cool photos that you can make images. But the principle is it's not a high frequency. Like I was showing with the relay, it can take a 20 hertz make and break, but as long as you're belling it and you're doing it at the same time, you're growing the power output. And it's not energy, it's power that you need to focus on. Like energy is not created or destroyed, it's abstract, so energy is really an ability, and an ability can't be created or destroyed. It's just like everybody has the ability to produce gold, but it's the amount of time that you produce the gold that gives you the power to be an alchemist. So you have the ability to do it, but if it takes you an infinite amount of time to do it, it's just the ability. It's the timing that it takes you that gives you the power to do it. And then once you resonate that with the right frequency in the bell, you'll get power magnification. You just got to think about it as a different way of doing it. And, solid state transistors can't mimic a single pole double throw type of action that you need. You need that, you can't do it with the transistors. It's impossible.
Do you have a prototype, or are you working on something?
Yeah, I was gonna do. Well, I don't have it on me, but because I'm trying to get into electrics, I'm. Uh-oh, am I out?
Your video went out. You're still good. We hear you. Oh, there you go.
So I have to work on electrics because I have a limited amount of time to do that. So I have to focus on electrics, and then I'm going to do this series in the background to give each key that I've found throughout my research of over 20 years of research.
Wow.
This is a great key to start with, though. Boost belling, it's very easy to remember. You want to boost the voltage and you want to slam it into a separate circuit that oscillates. That's the first step, okay? Then you can get into reactive to active power conversion and everything down the line. But you have to understand this is what Tesla was literally doing, and not many people share this. You know, I've read Tesla's patents. I've done the research. I know what he's doing, you know. But
Awesome.
what I'm trying to do on that next stage is I'm going to take a vacuum canning method and make it silent, because buzzers, even at 60 hertz, like most people don't realize, even Tesla suggested 60 hertz because it's not the high frequency. You can buzz a relay at 60 hertz and get these, you can get whatever frequency you want off of it. It's just an RLC circuit that it's dumping into. So even if it's 60 hertz, it's still a low frequency, but you can make the end product frequency whatever you want. You know, so my next step is to take the relay and put it into a vacuum, because a vacuum is a really good dielectric. It makes it silent and it makes it efficient. You know, so, and then when you drive it with a pulse width modulator, you can control the frequency and the duty cycle like he was doing, because he really did invent duty cycles off of those electric circuit controllers. That's what he was doing, is controlling the duty cycle with those. So it takes a little bit of understanding to gradually get to what he was doing. But I just want to drop the seeds and get it on record. And in the background, I'll do electric experiments and stuff like that, you know, as occasionally as I can.
Yeah. So what is this? What are you going to call this?
The boost belling method? Well, the series, it's a series. So I have different topics, multiple different topics after this. Like I said, this is just the first key.
I see. You're just going through the theory and understanding the principles and
You have
concepts.
you have to understand it from the beginning.
Yeah.
I've contemplated at least 6 keys after this.
So let me ask you real quick, the ring, is that where you're saying the power is?
Yeah, like he said, it's so that what you want to do is boost, like using a boost converter to boost the voltage on the capacitor, because it's the energy stored in that is the square of the voltage. Okay, so even if you put capacitors in series, you're squaring the voltage but halving the capacitance, if that makes sense. Okay, but as you're halving the capacitance in that series, you're squaring the voltage. So eventually you'll actually get more energy density by putting them in series. Like, everybody thinks you need supercapacitors because of the high capacitance, but the energy density comes from the pressure, the voltage, because it's the square of that. So it's not a supercapacitor that you want. You want a high voltage capacitor, a good dielectric, one that's thermally conductive when it comes to cold electricity. It's the pressure. It's the pressure that makes the difference in the energy density. But you gain the energy density, and like I said, that's only a voltage doubler that I was showing. And then you quickly release that energy into an oscillating circuit. Once it's oscillating, it's analogous to his hairpin circuit. And that's the next key, is how to convert the reactive power into active power. Tesla called it the method of concatenation. But there's modern ways with diodes, because he didn't have diodes, that you can do it easier.
So hold on. Is the energy traveling through the air medium or the earth ground medium?
It's both. I mean, he basically used the earth itself as the bell. Okay. And he was able, in that patent that I showed, the art of transmitting electrical energy, it shows exactly what, like, his frequency's off a little bit by the Schumann resonance, but it's because the waves that he was producing, standing waves, actually travel at pi over 2 times the speed of light. So they actually travel faster than the speed of light. And that's what people don't get. These standing waves travel faster than the speed of light. And he was working with standing waves. It's not transverse electromagnetic. It's magnetodielectric. It's longitudinal waves. They're not transverse. They're like sound waves in the ether, and they travel faster than transverse waves.
Yeah, doubling the speed of light actually can fit in physics, because we don't know the one-way speed of anything.
Yeah, it's a wavelength and frequency relation, really. It's not a speed. And when you do the wavelength and frequency relation on that, it's pi over 2 times that speed. You know,
So I'm speaking just of when people hear the speed of light, they say, oh, it's 300,000 kilometers a second, or they'll convert it into miles, and they say that's a cosmic speed limit. But that's the two-way speed of light, where we can only measure when it hits one object and then comes back. And then what they do is they take the average of the two trips and say that we have the speed of light. But we can change the speed of light one way to be infinite or instantaneous, and then the return trip of the light to be half of c, or half the speed of light. And when you average the two, you get the speed of light. I'm probably not doing this very well.
What, like, if I can say, like, he went to Hertz himself, because what we measure light by is the Hertzian transverse wave. Okay. He went to Hertz and proved that there is a longitudinal wave. If you know how to produce the longitudinal wave, primarily from Tesla's hairpin circuit, but you have to add inductance in the beginning. If you rewatch it, I showed Tesla's hairpin circuit where it was producing longitudinal waves with the hairpin circuit. Those, and he proved to Hertz, and Hertz was basically like, dang, Tesla, you know everything, like there is a different transmission mode that is faster than the transverse mode.
That's interesting.
It is like sound waves in the ether. That's the closest thing you can call it.
Yeah. Very cool. I was just watching a lecture where this famous physicist, mathematician, I think he's a philosophist, and he was just taking apart the Standard Model. He was just taking apart quantum physics. It was just crumbling. How it's like a lot of math tricks, and it just, science doesn't really take a step back and try to think outside the box. And I like how you're thinking. I like how you're just going into places that scientists aren't going into.
Well, I've put the effort in to really study this for 20 years. And it's not me, it's Tesla. And everybody that stands on the shoulders of giants, you just have to listen to what he said. And it's all just getting, it's not like everything that's mainstream is not at all like what Tesla was saying.
Yeah.
If you just go step by step, like I've read almost every patent. When it comes to his motors and things, I kind of skip that portion. But in the end kind of patents, where it comes to the power radiation and understanding why his system is different, I know why. And everybody that says they know why doesn't know why. I know why. I do, and I'm not trying to gloat or anything, but I'm trying to share it. Like, Tesla was right. It's not me, it's Tesla. Like, he laid the foundation. Yeah. And you just gotta know exactly what he said, and I can break it down easier instead of having to do the research that I've done. I can tell it,
It's funny because he was hardly ever proved wrong. So when you're looking at his stuff, if he's right 99% of the time and you're looking at 1%, you can guarantee it's right. And that's what's fascinating about him. It's just that's
the only way to prove a theory is by predicting experiments. And he was able to do it in his mind so well because he understood it so well that every experiment that he built in his mind just got better and better because he really understood it. and
Yeah,
it's
we're
a
still
different way
using
of
his
thinking.
technology today, so that's just a
Oh.
testament to how intelligent he was.
Right, but we
see-
have to start investigating the longitudinal mode of power transmission more than the transverse, because that's the next step.
For sure. Yeah, I agree.
if you wanted to recommend a patent, a Nikolai Tesla patent for people to read to get their toe in the water of what you're talking about, what would you recommend?
I would recommend his ozone patent.
Ozone?
His ozone patent. I can look it up real quick if you want.
Sure, yeah, it'd be great to get the number.
And
Yeah.
then directly following that, he shows how to use variable inductors and stuff to tune it correctly.
Nice.
Let me
Yeah,
look it
that'd
up.
be good.
I'll be right back.
Okay.
So, in the chats, what we got going on?
Oh, everybody loves this, man. We're all just kind of being quiet, listening. That's what's going on. You know what I mean?
Yeah, I'm glad I didn't do my presentation after Jarvis's. I'd be like, oh man, I can't follow that.
Is this the number here, Jarvis?
Oh, awesome.
568177A.
I have a book of all his patents. I'm going there.
That's right, Nathan. Yes.
All right.
And it's
cool.
funny. It's funny. The more important one after this is to get an understanding of it. The more important one after this is number 69. And I don't want to make a joke about that, but he was a Cancer, and the sign for 69 is Cancer. And it's just his 69th patent is really where it's at. But this is a good introductory to understand what he was doing. His ozone patent, because if you think about it, if you can make ozone, you can make nitric acid too. Fertilization is what he was really into. You can literally take the air and fertilize the earth if you used a system that basically uses no power. You use the air around you, and you can make fertilizers. And nitrates are explosive, potassium nitrate, and blah blah blah. But potassium nitrate is important to feed people, and you can just use a system like this to produce fertilizers.
Yeah.
So that's why it's really important, and to understand why it takes so much less energy to do what he's doing. And
So, I'm sorry, real quick. The longitudinal waves go through Faraday cages. They do, don't they?
yes, yeah, they're like sound waves in the ether. That's all. Like,
So hold on. You're talking about longitudinal waves. Now, the energy I create does the exact same thing you're describing.
yeah, yours produces both. I mean, a lot of systems produce both, but you have to, like, okay, if you're calculating for transverse, you're missing it by pi over 2. You know what I mean? So you have to do a different calculation to actually pick up on the longitudinal aspect compared to the transverse. The only difference is it's pi over 2 times c. So
Yeah,
it is a little bit of.
Sorry, I was just going to say it. Okay, less energy to produce it. Yes, builds out like a gas. You say sound. I always say it's like a gas. It just fills everything and it goes through everything.
Yes. And okay, to kind of understand it a little bit better, just think of the difference if you were to take a gas of atmosphere and compress it, and just a magnetic field. The magnetic field is going to have no influence on that gas, but an electric field will. Okay, so the electric field is more for the environment influence. The magnetic field is like on a different level that really just penetrates without any action on that gas.
Right.
Oh my God. Okay, hold on. Now let me give you something real quick. I keep telling people my gravity flyer is making fields, right? The two different waveforms that I use is that rod down the center, which presents like the gas, like you just talked about. And the second one was static electricity. So mostly voltage, very little to no amps, right? So those are the two fields that interact with each other. One holds in the other or pushes it away.
And one acts more on matter and one acts more on ether. The magnetic field is more etheric and the electric field was more materialistic.
Oh, I think I said that.
Oh,
Did
by
you?
the way,
Yeah, on the presentation. No, you said better than me.
so
Yeah,
Sean,
it's fascinating once you start understanding it. You know,
no. I got it.
no,
I've seen it.
No more
That's why-
explaining.
yeah,
I built it, and it was exactly what it does. And it's nobody really sees it. That's the thing. They've never built the field, so they don't understand it. You know what I mean?
could I show his 69th patent?
Yeah,
Because
absolutely.
that's where
Throw it
he-
up there.
he regulates it with this one. But the ozone is where I'd start for anybody getting into it.
Sounds good.
But all right, I'll try to do a share screen real quick.
Hey, Sean, just so you know, that device we were talking about earlier,
Yeah.
it's going to work so well the way we described, right?
Yeah.
Especially with what he said. So I'll show the device in a few minutes, but
Oh, you're going to share it?
yeah, zoom in a little bit, can you, Jarvis? I just want to see the patent number on it so everybody has it.
Is it visible?
Yeah, you can see it now.
Hey, my dog's giving me a hard time. I'll be right back. Sorry.
Okay.
You're fine. You're good. So do you see this this coil here? This is often referred to as his extra coil. Okay. What he's doing is he's actually taking a DC current from A to B. He's not working with AC at this point. He's taking a direct current.
Mhm.
He sends the direct current through the coil windings of a motor. Okay. And that goes through a circuit controller right here that he calls, and then it completes the loop. Hold on one second. Completes the loop down here and comes back up. So what he's doing is he's coming through, going through the motor coils, goes through a circuit controller to the other coil, and it completes the loop. And it's also going through this variable inductor here. It's actually easier for me on the other pattern, but he's using this to increase the inductance of the direct current path. He wants as high as an inductance as he can on that direct current path. And then the circuit controller opens that circuit. And when that circuit's open, it charges this capacitor to a really high voltage, thousands of volts compared to, like, say, this is 12 volts. And if it's going through this large amount of inductance and then this were open, it charges this capacitor to a huge voltage. And that's what you want as the first step in the boost bell. You want to boost the voltage on a capacitor because the energy is proportional to the square of that voltage. Then whenever it shuts again, it goes through this low impedance path through this primary coil, and it oscillates between the capacitor and the primary coil. And he has a loose coupling here that has a high frequency, high voltage on it to run his loads. So the first step is to boost the voltage on the capacitor and then short circuit it through a low impedance path through a primary and let it oscillate like a bell. And then that is what induces this high frequency, high voltage current. And especially if this is a quarter wavelength of the frequency that's produced by the oscillating circuit. Here he shows how to control the inductance with a variable inductor on the first stage of the boost bell, because you can control the inductance much easier in the first stage. And then once the switch is flipped, it increases the voltage on this and it short circuits, but you can control the inductance here. Here he shows.
Is the oscillations managed by the variable inductor?
The variable inductor is to basically get the voltage he wants on this capacitor.
Oh,
By
okay.
varying the inductance in the first stage, he can control the end product voltage that's winding up here.
I see.
So it's basically to control. This really has nothing to do with any of the oscillations, the variable inductor. It's just to control the voltage on the capacitor.
Wow. Okay.
And he called that his extra coil is what I'm saying. That's what a lot of people don't understand what his extra coil is. He's increasing the inductance as much as possible on the first stage to boost the capacity, the voltage on the capacitor. So you boost and then you bell. Okay.
Interesting.
Hey,
So-
Jarvis, you
Yes.
do realize this is the exact way that Gravity Flyer runs, right? Everything that you mentioned in there is what he's using.
But you can't do it with a transistor. You just can't.
No, I understand what you're saying. I'm just saying that that's what he was doing. The whole thing was putting the rod in the center and moving it up and down. You can change the
Yeah.
frequency with it, and you can change the amount of energy going into the capacitors very easily with that.
Exactly. Like you were saying with those coils, they were a little bit under inductance, and you were saying you may have to add windings to it. You can experiment with some coat hangers, iron coat hangers, and control. You can increase the inductance by putting an iron thing in there without having to add windings to
Oh
increase.
no, I threw a rod right down the center, Jarvis, and I put it right in resonance.
Yeah. It's once you do that, you're messing with the inductance, and that's how you would increase it. You know, to decrease it, you would have to take some windings off, basically. But okay, and
Go ahead.
this one, so he's showing here the same thing, but just using the motor as the inductance. So, and you know, this is the hairpin circuit basically, but nobody uses a motor or a high inductance coil as, you know, basically a choke, because it'll allow the DC to come through, but whenever it's oscillating, those high inductance block that high frequency DC. So the high inductance on the motor is important for two reasons: to boost the voltage on the capacitor and to act as a filter for the high frequency bell that's going off, because he didn't have diodes. Like we would add a diode right here just to solve that problem. But he had to go through a high inductance and then charge the capacitor and then short circuit it through this primary. And by using a very small capacitance here, he's showing it's not about the capacitance, it's about the voltage. That's why he's showing you can separate the plates here and actually get a better effect. This is a really low capacitance here.
Oh, hold on. You said that he used 60 hertz, right, as a driver.
Well, he suggested 60 hertz for the American American system.
Because he's running it through the motor, it's going to come out. You know what I mean? If he sets it at 60 hertz, right?
Right.
Then when you take the extra coil and you put the rod down the center, you change that frequency completely, because you're bringing it up to high frequency with all the different coils, and then you can change the amount by putting the rod in the center.
Mhm.
So that's how he's building it.
Yeah.
We're
And-
using MOSFETs and a tank circuit. He's using this.
Yeah, like, and with his hairpin, everybody makes the mistake of not adding the inductance either through a motor like he's doing here, or even just through an inductor like he shows here. But the point is, you just want a really high inductance and then rapidly open that inductance to charge the capacitor, because Steinmetz said that the voltage on that is dependent on the rate of change of this opening. So if you rapidly open that while the magnetic field is at its maximum, this will get thousands of volts on it. You know, so the first stage is to have it go through an inductance and rapidly open the switch to get the high voltage on here. And that's the secret. I was just showing a voltage doubler on mine, but the secret is send it through as high as an inductance as you can with as low as resistance, and then open that switch and charge a capacitor. That's the boost stage. Then when the switch shuts, it produces the bell, but because of this inductance, it blocks that high frequency DC or AC. But we can do it with a diode right here very easily to block the AC. I'm sorry. You know, but that's what I just want to get into your brain right now off that video is boost belling. Just think of it like that. It's an easy way. You want to boost it and then you want to bell it, but you can't do it with a transistor. You literally have to have I'm trying to get back to it. You literally have to have an opening. Like I use a single pole double throw relay. So as it opens, it actually shuts in a separate circuit. So the whole battery supply is isolated. And as it's belling, it's belling without any power supply. You're just literally striking and allowing it to ring. You know, so you want that connection. And then when you open it, you get that really high voltage on a capacitor. And then you put it into a separate, like he said, short circuiting it into a tank circuit.
So like a spark gap.
You can do it with spark gaps, and like I said, that's how he progressively got to the point of making his circuit controllers. But his circuit controllers were more geared towards what I'm saying, where you open it and like literally boost and bell it into a separate circuit. You can't do it with the transistor because it's just open, close, open, close, open. You know what I mean? It's not open and then transitioned into a separate circuit.
Right, but a contactor is just a fast spark gap, so it would do the same thing, right? This contactor quick send it off and then let it out, and it can't go back.
Yeah, he started with commutators, and then he went into spark gaps, and then quenching the spark gaps. But you have to quench the spark gap in order to get that high voltage to charge the capacitor, and then it fires again. So just using a spark gap is not adequate. You have to actually quench the spark gap so that the capacitor can recharge. It's the braking that's important. Just like on a mousetrap, whenever you set it, it's that brake that snaps it, right? It's that brake that's important in that situation. So the spark gap, it could just oscillate, and if you don't break it to recharge the capacitor, it's useless. So if you use a spark gap, you have to try to quench it.
Okay, so somebody keeps asking, why can't we use MOSFETs? Is it pushing back into the MOSFET and saturating the field and ruining it, or what is it doing?
Yeah, whenever it's belling, that back EMF will just blow it up. Like it's not allowing the reverberation of the bell. You're forcing the oscillation with the MOSFET. Okay, you're pumping it and you're forcing it. Like I said, it's like hitting the bell, trying to hit it at a rapid frequency of its resonant frequency instead of just slam it and letting it do its own thing. Because when you slam it, it's going to come back on the reverberation and blow it up with a transistor. You're going to slam it, it's going to go through and then come back and just blow up the transistor because it's only meant to go one way. It's a one-way switch. It's not a double throw.
Gotcha. I was just trying to make sure I answer the questions in there. It's pretty important to learn that because we're losing all kinds of energy not using those.
Yeah, and you don't have to, like I said in the past, you don't have to worry about if it's an NPN or a PNP, and it's rugged. And if it's in a vacuum, it's going to be efficient. It's going to be silent. You control it with the pulse width modulator, and you're on the first stage of what Tesla was really doing with an actual mechanical style switch. Solid state, it just can't do it. Maybe one day they can, but physically they don't have the double throw mechanism that a relay has. So
let me just ask, because we're getting not true. So I'm going to ask this, okay? Is it workable but not as efficient? Or is it just something completely different?
Yeah. It's definitely workable, but the way it's used now wouldn't be the way to do it. Because if you take the analogy in the video where the guitar player is trying to tremolo pick it at the same rate as the resonant frequency, it's just an inefficient way of vibrating it. You're forcing it into vibration, and the vibration should just naturally happen, like plucking the strings instead of trying to tremolo pick.
I know that. I did a video on that, and it absolutely fries your MOSFETs in seconds.
Yeah, you literally cannot use transistors, MOSFETs included. I mean, it's a transistor. So
real quick for anything, I was doing the switching board, right, for the capacitor bank. And as soon as it's forced resonance, but the right one that you were looking for, it immediately pushed back on that MOSFET and it starts heating them up real fast. I mean,
Right.
I could run it for less than 30 seconds and that thing would be red hot or blown.
Right. You need, and Tesla suggested you might be able to use a fluid that just cracks. And when it cracks like an oil, okay, you could use something like that to get the vibration, and then the oil would automatically seal the spark gap. So it's an efficient way of doing it compared to just opening and shutting a relay switch. But you don't have to drive the relay quickly. Like even 20 hertz, 30 hertz, 60 hertz is all you need. But you have to think about the bell frequency and time them correctly. But you could use an oil, or you can use an electrolytic interrupter. There's several other, like a pulsing arc could work. There's several other ways to make it more rapid than 60 hertz, and you're going to get even more energy if you do it that way. But that's separate. You know, just start with the relay to understand what you're doing.
Okay, so real quick, if I took the spark gap and I put any kind of oil, like mineral oil, in there with it, and it basically at a little bit of distance it sparks and then immediately quenches, and then it'll get ready and spark again, right? Is that what you're trying to say?
Yeah, he said the perfect medium is one that cracks and then reseals itself naturally like an oil. So I suspect he was doing that, but the way he was doing it in his patent was, it's kind of a convoluted way of doing it. He had like a little spinning thing to open and close the circuit, and then the oil would go through and get cooled, and it would come. It would be pumped. So let me try to find it if I can. Well,
okay.
Hey guys.
Yeah, you may be able to just experiment with oil and try that. I mean, it could be an easier way to do it, but I think an electrolytic interrupter would be better.
Okay. Well, I'm just asking so people can try things. I mean, it's a cool experiment to just put a spark gap and put oil in there that it normally wouldn't spark through.
Right, but
You know
if
what I
you
mean?
can start if you start with the relay and understand what you're doing, then you'll know where to go from there. Like you're thinking, great, you know what I mean? You're thinking of the next step, which is what you want. Once you understand what you want, you know, you can take those next steps. And all I'm trying to say is to get you started, a relay is perfectly fine.
Okay.
But
Got it.
you know, you use it the way that I'm showing. You know what I mean? You're opening the whole battery circuit and you're belling it into a completely different short circuit.
Man, that's really cool.
Yeah,
Yep. Yeah,
very cool.
good stuff.
You gonna light up that Wimhurst and show us?
I got to get into electrics because I only have a year on the patent and it's almost 4 months now. So I got to get going on that. But I want to do that series in the background while I'm doing it, you know. But I'm going to be doing quicker videos of experiments and everything. And then the series will come. And like I said, there's like 6 or 7 different separate topics. But the next one will still be on the relay way of doing it. But cold electricity or endothermic current, telluric current pumps. There's practical anti-gravity payload systems. Like there's a lot of different topics that'll be in that series later.
Very
But-
cool.
Can you guys hear me?
Yeah, we can
Yeah,
hear you, Mike.
You can hear me fine?
Yeah.
Yeah.
Yeah, Jarvis, we're gonna have to push your series, by the way, man. That was totally an awesome video. And
Yeah,
we're-
really well done.
you're gonna have to come on and show us one every once in a while. You know what I mean?
Yeah, I'd love to. That's what I'm trying to do. Like, you know, because there are keys, and once it clicks, you're going to be on your own. And it's the knowledge that's more important. If we spread the knowledge, there's no stopping it. You know, I could show you literally how to do it, but if you understand it and it's simple, you know, like a boost bell, just think of it simple. And
Yeah.
once you understand it, you'll be able to use that knowledge to make whatever systems you want. That's the
Awesome.
goal.
Great job. Thank you for sharing.
Yeah.
Thank you.
Thank you.
Awesome.
I felt bad too because I know a lot of people are using transistors, but just explore relays. They're so rugged.
Don't
Just
feel bad.
try.
I like relays.
Don't feel bad.
I do feel bad though because most people don't, they're stuck on relays and they don't understand that it's physically impossible to do what Tesla was doing.
Yeah, you need the spark gap. Yeah. But you can't do it with MOSFETs. I've even tried SSRs. I've blown the crap out of them. It didn't matter if they were 100 amp rating. Doesn't matter.
Mm-hmm.
It's something really
Yeah.
special with spark gap.
Yeah, and the
I've been able to, utilize the relay switch to a point where I am getting those effects and I get a lot of current coming out. So,
right.
but
The
once
next
you
step.
do it,
Yeah, I agree. I've been investigating a long time. So, it takes a moment for people to realize that it's kind of in vain doing solid state if you really want the effects that Tesla is getting. Unless it's a quench spark gap or something like that. That's different.
He pretty much invented the rotary spark gap, and that's when he was really excelling in his high potentials.
Right. I showed that in the video where one of his patents, like the exploration he took, because his first patent was a commutator. Similar to Carlos Benitez, he used a commutator and he was able to close loop a system, but you need 2 battery banks in order to do it. So you can do it with a commutator is basically a rotary relay. It's a relay that's just spinning.
Same thing, just a different design. Yeah.
Mm-hmm. And that's the first thing he tried, and then he went into the quenching mechanisms. But I showed a long list of his electric circuit controllers where he was using mercury and very advanced stuff, and that's where people don't even know about.
Yeah.
But that's the reason he was doing that, was to get the standing wave effects and continuous wave effects more efficiently. And just think, no semiconductors back then, so how would he have done it? Just try to think like that.
Well, that's exactly it. All he had was brass and wood. He didn't have diode. He didn't have that. He had to make capacitors right from scratch.
Yeah, it's more of a technique. It's
like
more of a technique.
Even the terminology was different back then. They didn't call it capacitors. They call it condensers.
Exactly. Yeah. But once you get it, it's gonna really expand your horizon. You're gonna be able to make your own systems, and that's my goal, is to help you understand the keys.
Yeah, it's gonna help because I'm gonna need it. I wanted to show you my new project here because I think you would really understand what I'm trying to do here. So give me a second. Let me pull this up. So what I'm doing is I'm taking the rod down the Tesla coil and putting it directly in the center here. Now, the little bumps are all magnets, right? The yellow and orange spheres there, they're going to be full spheres. Anyway, they'll rotate together in one direction. The blue one will rotate in the opposite direction, the same as the center rod. And it'll run right through a Tesla coil, that rod right there.
I'm sorry.
Yes. The rod runs straight through that center of a Tesla coil, right down to the center thing. So I'm directly putting that energy we just talked about in there. And then I was talking to Sean about electrics and the high voltage ones you were making.
Yep.
And the system, you know what I mean?
The charge sphere. It's the charge density you want. Like if you're just charging the surface of those spheres, it's fine, but you're only going to get a surface charge. And what you really want in a system like that is the charge density. That's why I use, like, the analogy is if you use an inductor that's nowadays, they have a fine powder that's used in the inductor. It's the same with an electric to have a higher charge density within the volume of the material instead of just the surface. Because if you just charge anything that's conductive like that, you're just charging the surface and you're not getting a high charge density. When you use electrics, you get that volume charge density. You know what I mean? But what you're saying, just to go there, I absolutely agree. Let's see what happens. And if that's on the ball, then we can make it better with our electric patent.
Well, check it out. So I could say this: if I even just made them empty and filled them with sand, based on what you were doing with the sand and making the electric, right? Out of the sand, you can still pick up a heavy charge on each one of these spheres that same way, right?
Yes. Yeah, think of it as the surface area, just like when it comes to graphite, or like the thing that makes graphite so important is all the little caveats that the charge can cling into. It's the same thing if you use sand or even a nanoparticle. When you get down to the smallest, it's going to naturally increase the charge density, and the charge density is what really matters the most with gravity. If you want to control gravity, you want a high charge density. And most, like Sal Pius, and they keep saying, they can't get above, they can't get a coulomb of charge. And using my methods, that's why I want to get into it really bad. But using my methods, I know I can get a coulomb of charge because, it's dependent upon that granular aggregate that I'm using. The binder is going to help solidify the charge, but the aggregate is what adds to the density of the charge.
Gotcha. See, I was thinking that in the earth, you got to have places that are magnetic. You got to have places that are static. You got to have places that run that same energy that I am, you know what I mean, through that Tesla coil. They all have to be in there in order to get gravity, because the earth naturally builds them. And the fact that this stuff doesn't go through mineral oil, which would tell me it probably does not go through crude oil, so that there would be spots in the earth that it would not penetrate and would not go out as a field. So it'd be a weaker field on your magnetosphere. You know what I mean?
It's actually because the oil absorbs it like a sponge. It's not that it can't travel through it. It's storing it. Like if you look up a dissectable capacitor, really? Yeah, you can take the metal parts out of a dissectable capacitor and just leave a glass, and the glass will remain that charge because it's stored in that. And then you can put it back together and discharge it. It's not that it can't go through. It's just absorbing it and it's storing it. It's a dielectric.
Stored in a dielectric. Yeah.
Mm-hmm.
Wow. Okay. I'm learning.
That's the great part about the dielectric. The dielectric, you can store electrostatic potential in that for a long time, and as soon as you discharge it, it will come out in huge velocity and high amperage. That's one. If you short out a capacitor, you're going to get heat. You got instant heat. Like I've done it with my fingers, and I've actually almost like welded my fingers to the capacitor because it discharged so hard at so many amps. I even saw the wires go red. So
yeah. Did you see that video, Mike?
No. Which one are you referring to?
I just played it earlier, but yeah, a lot of people nowadays think that you need a high capacitance, but that's really not what you want. You want a dielectric that can withstand the voltage, because the energy density is the square of the voltage. Right. It's the square, So, you don't need a big, large capacitor bank unless you're trying to store energy. What you want is a dielectric that can withstand a high voltage. That's key when it comes to energy density.
Yeah. Yep.
So, what would you suggest for the first time running this thing? Would you suggest trying to make the spheres themselves electric, Or would you say try sand?
I would say try charging it like you're thinking, just to try because those are more difficult. If you get any results by just surface charging it, then you can go to those other steps. But honestly, I would just use my method of propulsion. I have a different method of propulsion. So, but I'll get there later in the other keys, you know.
I'm trying to. There was a guy who's doing this, and I read his PDF and checked it out. And he was going to use different types of energy, and I thought this energy we created out of the Tesla coil would be perfect for this because it builds out so well. And then
honestly, I kind of see more of this being used a little bit of a time dilation thing, and I know it's related to gravity, but maybe that would be the better experiment than seeing if there's a weight reduction, is seeing if there's a difference in time. If that's the case, then highly charged electrolytes like me and Sean are working on it would be the next step.
Yeah, I had an idea kind of similar to what you guys are talking about. If you charge up the dielectric constant in the space around your device, okay, you get that highly charged. And then what you do is you get the end machine, which I built a scale model of Bruce De Palma's machine, and you start spinning it at a high RPM. He actually took an analog clock and put it at the axis of the axle that's spinning the magnets. He was getting time dilation.
Mm-hmm.
So that proves that a rotating magnetic field. Now, at that time, he didn't have the means of charging up the dielectric field around that space. While he was doing the same experiment, he probably would have got better results.
That's why I'm thinking the electrolytes are the next stage in our technology, because we're just now breaking open that field. And in order to do it the most efficient way is the way me and Sean are doing it. And that's why I
Go ahead.
And like I showed on my first presentation, Nikola Tesla had a dynamo, and it wasn't like Bruce De Palma's where it's unipolar like Faraday disc. It was two, spinning, and I was using a fluid, and I call it a hybrid. Whenever you use a high current generator like that and tie it into a high voltage generator, theoretically, if you do it correctly, you can have any voltage and any current that you want in a system like that. Because it's a hybrid. You got the voltage on one side, say like a Wimshurst, and then you got a Tesla turbine or a Tesla fluid dynamo on the other. And if you time together correctly, you get something like the Testatica that actually powered a community. So hybrid systems is one of the topics that's key too in the future that I want to discuss. But it's because people got to start at the root. They got to know what they're doing. But hybrid systems is where it would be for a home type of power system, in my opinion.
Very cool. Good stuff. So it's about that time, good people. I had a blast, but my carriage has come. I'm turning into a pumpkin.
Sean, thank you for everything today, man. You're awesome. Presenting, hooking us up with some cash for the builds, man. You're awesome, brother.
That was really great of you. Thank you, Sean.
Appreciate it. You guys are awesome. See you, Jar Jar.
Yeah, buddy. I'll see you, man. We're gonna have to get some work done.
Yeah, we do. All right, much love, guys.
Nice. Have a good night, everybody.
Thank you, Sean. Well, if there's any questions in chat, I can answer a little bit, but I gotta jump off here soon too.
Yeah, I think we covered that earlier. Everybody was asking the stuff in there.
Yeah, it might take a couple of times to watch that video, but I really feel like that is a good first step for beginners, is to understand what I was trying to get at there.
Yeah, it really, that and talking through the patent really helped. because there's things that I see all the time that I don't know how to, explain, and it's all right there.
Mhm.
It's not like I did anything new. I just did what he did in a different way, maybe. You know what I mean? But I
Right.
got there.
Have you guys ever heard of the Steinmetz dynamotor?
Mm-mm.
Yeah, you might want to look that up. Steinmetz designed a motor generator back in the early 1900s. What it does is it runs off the actual power grid itself. So it's actually using the power from the power grid, powering itself, creating more energy, the output, and then feeding it back into the system that it's getting its power from. So this was used for quite a while in the early 1900s. And all of a sudden, they just started disappearing. And that was kind of like your first online over Unity free energy device that was used, in industry. So it's something you might want to look up. And also the
You said
motor too. It was Charles Proteus Steinmetz. He designed it called the Dynamo.
yeah, Steinmetz knew what Tesla was doing with the rate of change. I've been trying.
Pretty much anything that Tesla made, Steinmetz perfected it and had the math to back it up.
And the slew rate is what I went into in that video too, because a lot of engineers don't even know that word, but it's the rate of change. It's not, energy is always going to be equal to what goes in and out, but power is not conserved. You can have higher power out than in. We have classic examples every day of that, so don't think in terms of energy, or else you're going to be a dog chasing your own tail. I mean, it's obvious, it's an ability. It's the power that you want to focus on, not the energy.
Yeah. All right, guys. It's been about 2.5 hours. Jarvis, thank you, man. This has been
Thank you.
awesome.
Yeah.
Yeah, thanks, Jarvis. This is awesome.
Yeah, good work.
Thank you guys
Great
so
stream.
much.
It's good to
Thank
see
you, Mike, for
somebody-
coming on.
Yeah.
Yeah.
Oh,
I'm glad
thanks, Mike.
somebody's
Yeah.
playing with this podcast.
If you get a chance, Mike, try to watch that video. It kind of went over exactly what you're saying. You're like me. You've done a lot of research. You know what you're talking about. I mean, you, Nathan, me, and Sean and Ben on that one link is like almost 100 years of research, and it's great to have that available to people. We'll get them to understand eventually.
Yeah.
I tell you what, seeing it in your lab will make you understand real fast.
Yeah, that's the best way to do
Yeah, that or blowing up about 300 MOSFETs.
it. Yeah, but when you blow them
Guilty.
up, you're doing it right when you blow them up, because I was saying, like, you can't do it with that. When you're blowing them up, you're doing it right, but it just can't handle it.
Well, guys, thank you very much. I want to thank everybody in the chat. You guys have been really awesome tonight. Thank you guys for doing everything. And I want to thank Chris right here for the memberships, man. Totally awesome.
Yeah,
Thank
that
you,
was really
Chris.
cool.
I want to also thank Sean, Big Spender, taking care of us, giving us cool material, man.
Sean
Sean,
sent me one, so yes, I appreciate that, Sean, as well. That he didn't have to do either of those, and
No, he
that
didn't.
was very generous of him.
yeah, I think Chris gave 2 memberships. So
Yeah, he
that's
did.
awesome.
Yeah, I saw that. That was really cool too. And then I think one of my viewers, Jalapeno, got one of the memberships. I think that's why he was excited. I hope he got it, because he's a big fan. So
I think he did. Yeah. Awesome.
Right
guys.
on. All right, guys, thank you. Have a great night. I really appreciate everybody.
Have a
yes,
good night.
appreciate you guys.
Take
Have a good
care.
night.